Welcome. In this session in linear data analysis, we'll explore the curse of dimensionality for data that are uniformly distributed. What we mean by that is in statistics, we usually suppose that we have some variate, and it's usually the symbol x, and it has n entries. How can we get that? Well, in our case, we're given data, and they're in a matrix, and they're all real numbers, and we have m observations and n variables. Now, let's suppose that we have one of these columns, and what we want to do is cause this column to be distributed between the value -1 and +1. That's the assumption that we need for, part of the assumptions that we need for uniform distribution. Well, we can calculate that as some vector c. What we do is we take our original data vector, and then we subtract the minimum value that we find in that, and then have to multiply it by the ones vector. And then we scale that by the largest minus the smallest. So this fraction is now a number between 0 and 1. If we multiply it by 2, it's a number between 0 and 2, and if we subtract the ones vector from that, we now have every entry of c sub j as lying between -1 and 1. And what we'll do is we'll take this statistical variate, which is x, and we'll suppose that it's a row of c, and then we transpose it. So what that now means is that each variate can be represented. So each variate is an entry of x, and x is a transpose, because that's how statistics likes to do things, and this will vary between -1 and +1 because of our normalization formula. Now, what's the effect of this? Well, what we usually do in statistics is we assume things are IID, and that means that each of those variates, in our case columns, are statistically independent and that they're coming from identical distributions. The question is, what is that distribution? So what we'll do is we'll consider a uniform distribution between the value -1 and +1 after we've performed our normalization of our data. What this does is this spreads our data uniformly in a hypercube. It may have come a bit larger or a bit smaller, but after we've normalized it, it's now within a hypercube, and we're going to suppose that it's uniformly distributed within that hypercube. Now, how big is that hypercube? Well, a hypercube has a side of 2, so if it's in n dimensions, that's 2 for the first dimension times 2 for the second, and so on. So the hypercube volume is 2 to the n, and that means that the volume of a hypercube is growing exponentially with the number of variables. What if we have a general size d? Well, we can use the same kind of reasoning, that it'll be d for 1d, times d for 2d, times d for 3d, and so on, and we'll get a d to the n. Now, let's suppose we want to answer this question. What size of d has half the volume of a unit hypercube? Well, this means we're going to have to solve this exponential equation, right? So we have to remember that if we have any base beta and we raise it to the n, that is e to the n times the natural logarithm of beta. And that means what we do is we say what d has the property of d to the n is 1/2 of 2 to the n. And when I work this out, I get d is 2 to the power of 1 minus 1 over n. And I immediately observe what happens to this exponent as n goes to infinity. Well, as n goes to infinity, 1 over n goes to 0, 1 minus 0 goes to 1, and that means that this d will approach 2. And immediately I'm going to get a little bit suspicious, so I'm going to work through a little more arithmetic. Okay, so I have a unit hypersphere, right? And now I have something that's size d, and that d has half the volume of the unit hypersphere. What's the thickness of that shell on the outside? Well, that would be the width of the hypercube, which is 2, minus d, and then the shell is half of the width. So that thickness would be 2 minus d over 2. Now, how does that shell thickness vary with the number of variables that you have, with the dimensionality of the hypercube? Well, I'm going to plot that. So what I find is if we were in one dimension, then the hypercube, which is just a line segment, has a width of 2. D would have a width of 1. 2 minus 1 is 1, divided by half, is 0.5, and sure enough, I get 0.5. As I go into 2D, the thickness is dropped to be 30% of the size of the unit length of each edge of the hypercube. Then in 3D, it's less than 20% of the edge length, and so on. We can see that this is an exponential decay, and what will happen is the thickness of the hypercube, the thickness of the shell around a hypercube goes to 0 as n goes to infinity. What that means is that the volume that contains half of our uniformly distributed data is in an infinitesimally small shell as the number of variables increase. This is highly counterintuitive, but what it means is that if our data are uniformly distributed and we have high dimensionality data, then most of the data are living in a thin little shell near the edges of a hypercube. So uniform distribution is a very common assumption in data analysis. What we're discovering is that the data are concentrated in a shell of a hypercube. As the number of variables increases, the central portion of the hypercube will tend to contain 0% of your data. That means that this is really not intuitive, right? And the shell will tend to consume 100% of your data. The inscribed hypersphere, by the way, if you put a hypersphere inside a hypercube, its volume also goes to 0. So that means that everything is living in these corners between the hypersphere and the hypercube. And our intuitions, once we get into statistics of high dimensional data, our intuitions more or less can't be trusted, and we have to rely on the math. So in summary, for this session, what we have is a uniformly distributed version of the curse of dimensionality.